So we are with Josef Whitter, Director of Protocol Engineering at Informal Systems, and he leads the whole auditing system or he leads the whole auditing service for Informal. So I guess Joseph, introduce yourself and Informal and just auditing in general.
Yeah, thanks for inviting me. I'm not actually leading in terms of sort of management or anything like this. I'm sort of on the technical side, participating in the audits, and also I think shaped a lot the kind of work that we are doing, just the way I do things. So yeah, my background is I have a long academic background. I would say I worked at universities on different areas that I think are quite related to this area, to auditing and to the blockchain space. So I worked on distributed systems, wrote my PhD thesis many years ago about consensus, partial synchrony, these kind of things that are sort of at the core of what we're doing here, and then during my academic career, also moved towards formal verification. So we did also model checking, particularly of distributed systems, of fault tolerant systems, and sort of these two things led me into the space because the guys here at Informal figured out that this might be interesting skill set to have. So I joined the blockchain space in 2019. I have been involved into the design and specification of the Tendermint Lite client back then. After that, we also did a couple of other specifications, analysis of distributed protocols. So yeah, I've been with Informal basically since the beginning of the company, 2020, and yeah, so that's I think a very nice continuation of sort of my work on distributed systems and formal verification. I always my goal has always been to reason about the correctness of systems. There are people who are very much inspired by writing nice programs, or people who like to squeeze performance out. I really try to understand that, make sure that the systems are predictable. If you're designing an engine for a car, you want to make sure that your gear wheels are strong enough to maintain the momentum. My idea was always to sort of make sure that the systems are working. Yeah.
And so, did you get into distributed systems from the crypto side of things, or like before it was cool but still crypto, or like not even crypto related?
Not even crypto related. I finished my thesis in 2004 on consensus. So back then, I think all the people who were working on this thought it's like a theoretical topic in theoretical computer science. And then came blockchain. Then came also sort of Tendermint that basically brought sort of the classical distributed systems, distributed algorithm theory into the blockchain space. And suddenly, this sort of weird fault tolerance thinking was the core of a big industry. Before that, fault tolerant systems and this kind of redundancy was very limited. You would find this kind of systems, in the space shuttle. There are not so many space shuttles compared to blockchains that we have now. You sometimes would find it in civil airplanes, where sort of high security and safety are an issue. But sort of the use of consensus in crypto and in building big decentralized systems came a bit after that. So yeah.
Mm-hmm. And would you say most auditing sort of like only really a crypto thing when it comes to sort of hiring people to check the safety of your code, or is auditing has it existed before crypto? Has it been a big industry? I want to get my mind around just auditing
Yeah.
in crypto versus not.
I think so. Auditing or security analysis or certification has a long history in certain parts of the of sort of computing industry in general. I mean, sort of the classical examples is like software that you put in cars or in planes. You demonstrate that it is reliable. And what typically is done there is sort of you have to come up with a big documentation. These are the requirements. This is the design. This is the implementation. This is what we did, in terms of testing, in terms of processes, in terms of review to make sure that the system you're building is actually good enough or that does the job. And then there have been certification authorities that sort of go through all these documents and sort of check whether you have done your work. So this is, I think, a very classical thing. I think security analysis also for, I guess, in banks and all this is very common. I think a big differentiating factor here is that in a lot of the computing industry, the code is closed. It's not accessible, right? So somehow, if you're running a bank or a banking software, you run it computer behind walls. You don't show the software to anyone. And so the only thing you want to make sure, roughly speaking, is sort of no one from the outside is able to get in, right? But here, a lot of because of the crypto ethos and because of you want to make sure that everyone is able to understand the software that we are running there, you're doing everything in open source. So you're also developing in open source. So also, if you're building in vulnerabilities in your code, everyone is free to look into your code and see them. So I think the focus is a little bit different to under other sort of parts of the computing industry, but it has been around for some time, as I would say.
Okay, and I want to better understand the nature of security when it comes to just like finding bugs from these auditing firms and services, and just the general market when it comes to hiring a firm, doing auditing competitions, hiring individuals. How is the philosophy or sort of process of auditing and the nature of not really knowing if it's really secure? You can't really guarantee it's unhackable. I just sort of want to better wrap my mind around auditing as an idea.
Yeah, I think there are two important things to distinguish in this process. So there are two big questions. So one question is, are you building the right system? And the second question is, are you building the system in the right way? So are you building the right system? Depends a lot on the environment where you want to run it. So it's very easy to imagine that you build a database. In the end, a blockchain is a database. You are sending transactions there, so that you can very easily build this database for one user. She's sitting in her desk, sends one transaction, make sure that the transaction is terminated before the next one, and this system can be correctly fine. It works. And the moment you do the same system, but you have 2 users or 10 users who at the same time send transactions and they're somehow interacting and interfering, it's breaking. So the system, which is fine in one case, is not fine for the other one. So the point really is to understand what am I expecting the system to do from the outside. So this is really on sort of the design side, on understanding the environment, the properties, invariance. And this typically is sort of, need some sort of a good approach to specifying and to designing systems. So that's the one question. And then there's the other question, which is, am I building the system the right way? So here we talk about code correctness, right? So once I understand what I want to build, do I use the right data structure? Do I use proper parameter validation? Do I use the right hash function for the requirements? So these kind of things. And but these are two different skill sets, right? So in principle, if you want someone to look at your code and want to make sure that it's correct, because in the end you have just one question, right? Is the system secure? You should look. It's important to understand that there are two different questions that you should address. And I think it's important also to understand the separation if you are thinking about audits, right? Because and different audit companies. Also, in terms of there's a lot of work you can do to make the work for the auditors easier, which also gives you more value for your money, right? If you have great specifications, design documents, and can explain why you believe the system is doing what it's supposed to do, and it's not doing what it's not supposed to do, the auditors basically can just follow that, right? If you don't have this, you already have to start to guess what this system is doing, and then it's also the work of the question asking, is the system secure, becomes more vague. If you don't know, secure against what, the question becomes more complicated.
And so with auditing you can't really ever say this is like impenetrable or there's never going to be a hack. So how should people think about auditing? Because you can never provide these guarantees, but they're helpful. But how helpful truly is auditing when it comes to hiring like individuals who might just put a stamp and go, okay, I looked over it, looks good to me, versus someone who really like checks everything and can give you more higher security assurance?
Yeah. So you're totally right. So first of all, there's never 100% assurance. That's the first thing. And the second thing, which is important to understand, is that in principle, audits are snapshots, right? You're giving a certain version of the software to an auditor. Typically the first step of the audit process is you send over your commit. And the thing you have to understand is that the moment you put another commit on this code, in principle, there's also the opportunity to include a bug at this point, right? So this is really in some sense, in the audit is a very punctual thing. So if you care about security, you should think about the whole process and at what point is the best way to involve the company. Going back to the the points of building the right system and building the system the right way, is with one commit, you're not going to most likely you're not going to change the whole design of your system, right? You're going to change details at some point. So if you have a clear understanding what you're building and what are the properties of each of the component, what they need to satisfy, you're already taking care of big part of the thing, right? It is really something which is going to be stable, right? Even if you change at some point the data structure of something in somewhere deep embedded into your code, it doesn't necessarily change all the guarantees or all the design properties that you're having. So this is one thing. So this design and making sure that the design is correct is something that is not necessarily punctual. This is something that stays, and that's also something that we at Informal try to convey in our audit reports. So even if clients don't have this detailed specification documents or requirement documents, we do this for us as a first step. We say, look, this is how we understand what the system is supposed to do, and these are the properties that need to be satisfied. And we also give this we write this down, we share it with our clients to make sure that we have a common understanding, and that's something which is stable. That is something that they can use in the future. And then also for these properties, we define what we call threats. So where we said this is a potential deviation, which could lead that these properties are not holding, and we are going through them in the analysis, and either we say have a finding where we say, okay, there is a problem, there's a bug. But even if we not find a bug, we are, if you say okay, we try often also to say, a little bit more. Okay, something like this actually holds, but it might only hold right now because you have this specific if statement in this part of your code, and you should be very clear about that. This, changing this might have big consequences. So also giving sort of explanations why the current version of the software is working also sort of can inform your future development and future steps. So ideally, sort of you get this out, and this is just a piece of information that anyhow, if you're doing an audit and review, you have to obtain. It's just as a matter of communicating it back, and I think that's also one of the things that we like in our audits to have interactions with our clients. We want to become part of their team for the time of the audit and have these interactions and try to help them. So yeah, coming back to your question, security is an ongoing task. I think there should be really a separation between the long-lived properties, the designs that they're likely not going to change, and they must sort of hold. And then there is this issue of sort of specific versions of the software, and then obviously this if you're sort of going to launch or you're going to do an upgrade, this should be looked at. Yeah.
Mm-hmm. So rather than auditing being like, okay, here's my code, it works or it doesn't work, like, is it going to be hacked? Instead of just like that one snapshot and a yes or no, it's more first defining the system as a whole, having the like specifications, and then the, I guess, open parameters and endpoints and all like the threats have to be understood. And then after that, you can sort of minimize a lot of these risks, have better understanding of the system. So eventually, whenever you need to change something, you understand it better to minimize those risks. So is that like a good understanding?
Yeah, totally. I think in general, the point is if your project is successful, you're going to change your code. That's the way it is, right? And you should be prepared for this. So if you want to optimize a piece of software, you should be on solid ground, right? You should understand why is it correct and what is the wiggle room for optimizations, right? I think good practice is also to have a lot of tests, right? If you have a lot of tests, that also helps you. If when you change your code and suddenly a test fails, you understand, okay, I've broken something. What's going on? So I think you need to sort of to plan for all of this, and also plan for security the same way. And yeah, another thing sort of that we are, and perhaps we're getting to this question also, is that the systems that we are building here or that people are building are super complex. It's not that they write one piece of code and that's it, but it's one piece of code that uses, I don't know, a smart contract environment, that uses libraries, that runs on some on some blockchain. So each project uses a lot of code, which is not written by the teams who are writing the code. So there is, and I think, or what we have seen is a lot of the time the vulnerabilities and sort of the problems, they appear at the interfaces, because you don't really know what the other side of the interface is doing, what it's expecting, right? Very often, all this, a lot of the code is sort of under specified, sort of in order to understand what to expect from this library to happen, you actually have to read it. So, and this is sort of not, it cannot get all the information of all the software you're using in your brain, but this is also for internally, right? Even your own system is built of different components, and you also have to understand how they interact with each other and what change in one component ideally shouldn't sort of interfere with some other component, right? So this also, I think, in terms of design and software architecture from the beginning, you should sort of make sure to understand your interfaces, the contracts at these interfaces, so that you're ready for change. I think that's a big part on the software engineering from the beginning.
So whenever you want to do an audit, you can't really just ask like for one large auditing. You have is there like layers to an audit, or I guess if you want to audit only specific parts, like how do you go through that process of figuring out what needs to be audited, what doesn't, the layers of the stack, those components, languages, all that
Yeah,
stuff.
typically, sort of course, people care most about their code in some sense, right? So they sort of when they ask us to do an audit, they limit the scope of the code that their team is developing. So I say most of the time, it's not always the case. But and so, but the challenge for us is that, of course, we have to understand it is not the whole truth, right? This piece of code is interacting with other pieces, with other pieces of the stack, and sort of we have to figure out what are the dependencies, what is important, what we can expect from the other side. I think that's also a matter of getting discussions with the client, what their sort of what's their view on this, and how they see this. And as I said, yeah, the a lot of the vulnerabilities are not within the code that sort of they are developing. They typically have a good understanding of that. So you have to figure out what are the sort of the interfaces. And yeah, it's also these dependencies. It's also part of the very often of this question of, are you building the right software, right? Sort of, do you really sort of the what you expect, the components you're interacting with, what you expect from them, is it justified that you're expecting this from them, or are they actually showing behaviors which is different from them, and you're not building the right system, right? So yeah, that's a big big challenge there. But yeah, typically together with the clients, we agree on how to approach this, and what we can assume and what we can not assume, right? Also, typically, sort of the other components that they are using have been audited either by us or by other companies. So we also sort of make sure to understand what is the sort of the status of the other parts of the software. Can this be trusted? How to also figure out whether the current version of the library has been audited. These kind of things. All this information we're trying to obtain. Yeah.
Yeah, because a lot of teams they just want to audit their smart contracts, but then their smart contracts interact with bridging and the module and all these other aspects. Could you talk about the development of, let's say, smart contracts on the application level, or modules which are like more ingrained into the system versus frameworks versus like consensus level testing? Can you just sort of describe the auditing process when it comes to different levels and different types of,
Yeah.
I guess, the stack?
Yeah. So I think there's so typically smart contracts are sequential piece of code, deterministic sequential piece of code, ideally, right? So in some sense, from the viewpoint of sort of complexity, or sort of the behaviors they're showing, compared to a consensus algorithm where you have like hundreds of nodes doing something in parallel, exchanging messages. There are a lot of different orders. On the smart contracting side, this is much more manageable. So you don't have this complexity. On the other hand, there's a lot of code typically. So the sort of the code size and sort of also depending on in which languages these are written, sort of this can really be a factor there. So you have sort of to take care of this. But this is like just the sort of the bird's eye view. In general, you still can have something like issues similar to concurrency. I don't know if you do a smart contracting to vote, for example, and you want to vote on something, and you want to have a majority of a group to sort of vote for something, right? Then this voting takes time, right? And then the question is, what happens if the group composition changes while the voting is happening, right? What is the majority? Is it the majority that sort of was there at the beginning of the vote, or at the end of the vote, or somewhere in between? So you have these things can, although in general sort of the code is sequential, if you look at it from the outside, there are something you have sort of interleaving of these operations. Like the vote is interleaving with the changing of the group composition. So you can still have concurrency issues there, but it's still much more controlled than on the consensus level. So yeah, that sort of I would say is the big separator there. It's much more code, I would say. Consensus is highly distributed. Consensus is designed typically to be fault tolerant. So I've most experience with BFD consensus engines. A lot goes into timing models, timeouts, different fault models. So this is sort of there's a lot of complexity here, and also a lot of again a lot of concurrency. That's not something that our mind is very good at. We are very centralized people, right? We are one person. We have a brain. We sort of this is the way we think. We do one thing after the other. And in consensus, you have hundreds of nodes doing something sort of at the same time. It's very hard to get into the mind. And therefore, for this kind of system, you should really, really have a good understanding. You should really have a separation between the protocol and the code. You should understand sort of what is sort of the high level view. How can I abstract it? What are views? What are rounds? What are messages? What are quorums? What are certificates? Without having each line of code in mind, trying to understand sort of the mechanism from this very high level viewpoint, and make your arguments about the correctness there. And once you have settled that, you sort of go into the code and say whether this thing is actually implementing what I have sort of envisioned in the abstract thing. So that's I would say more complicated from the sort of concurrency aspect. It's harder, I think, to grasp for human brains. It's also harder to grasp typically for any kind of formal methods or tools. It's just because there's a huge execution space. While on sequential code, you have all these, of course, data structures, sort of validation things, hashes, all these the kind of things that can go wrong, arithmetics, and so I think that's the sort of the difference there. And then, of course, on top of that, if you talk about bridges, you're putting another level of complexity, right? Because a bridge is basically a component, a mechanism that makes two consensus distributed systems to talk to each other, right? So you get a distributed system of distributed systems, which in general is super, super complicated, especially if you don't want to oversimplify and want to have a trusted setup. So if you really want to have a trustless sort of setup, that's quite complicated, and you should really sort of have a very sort of system level view how these things are working, and also really to have an understanding about what things can go wrong and what are you sort of doing in case of go wrong, right? If you build a bridge between two chains and one of the chains is compromised, what is the second chain's reaction to this, right? Are you able to secure some of the properties? So they're really I think the focus is much more on the protocol and on making sure that you get the properties right. It's first step. And this is sometimes very hard because people, I think, very often like to design systems while coding. It's their way of expressing their ideas. But I think programming languages are very it's very tough to reason at a high level because they're very, very low level. So, and similarly, again, if we think about audits, I think the typically what we see on sort of consensus level audits, it's much more on the side, am I building the right system? More on the protocol side, what are the assumptions? What are the timing assumptions? There's much more sort of conceptual work on trying to understand what the system, what are the components, how they are communicating. While sort of on the pure smart contracts, it's typically much easier, this kind of work.
So smart contracts are sequential and they're easier, but then you also have to like factor in mechanisms, which is like the money and people part of thing and how it all interacts with everything else. And for consensus, it's more well defined, but the, I guess, like edge cases are just way more complex. I want to get your. I'm assuming you worked on the Tendermint Go implementation, but also the Rust one, Malachite,
Yeah,
right?
yeah.
Could you talk about the differences in, I guess, having your first round with it and then again in a different language, Rust? So talk about the different implementations and then auditing around distributed systems in Go versus in Rust.
Yeah. So Tendermint in Go is in my opinion a very exceptional case in the crypto space. It's a piece of code that runs now for 7 years or something, right? And has turned from a sort of an innovative new product into a maintenance sort of project that also Informal System was stewarding for some time under the name of Comet. And there and I wasn't around in the beginning, so when I sort of joined the project, I was already it was already mostly done, or was already done, I guess. So I cannot really say something about the historical way how things are done, sort of came about, but it was, as you said, written in Go. And I think the programming language shapes a lot the way you write the program. And in Golang, sort of concurrency is very easy, and Go routines are very easy. So you end up to have a piece of software which is highly concurrent because it's easy to write. And very often it's not so clear whether you need this kind of concurrency. So what we tried in Malachite from the beginning was to avoid that as long as possible and stay single-threaded because it's much easier to analyze, right? If everything is functional and you just have, if you receive a message and until you get a response, everything is just functional. It's much more modularized. You can analyze it more easily. You can understand what are the pre and post conditions for each functions. So I think this is one of the learnings that is there, and so that's one of the separators. Yeah. The other thing is really that from the beginning in Malachite, we really wanted to have a piece of software which is testable. That's also was sort of going for in this direction to be functional as far as possible in the implementation. And also we wanted to reason about it in a sort of abstract way. So for Malachite, from the very beginning, we have written a specification in Gwent, which is our specification language that comes with the Rust implementation that basically captures the architecture of the of the design. Having said that, I think still Malachite is not like, of course, not as complete as Tendermint and Go was. If you think about, I'm not like evidence handling, these kind of things. There's so many sort of additional features on top of consensus in Tendermint and Go. So yeah, there are sort of different stages, and yeah. Therefore, I think in terms of auditing, because it's functional, and we wanted to be quite precise about all the interfaces that we're having there, I think we are have made the life of auditors simpler in that. But in the end, we made the work of auditors simpler by making our own work simpler, because we wanted to have it easily testable, understandable. I think that's the driving force there. Yeah.
Can you talk about sort of the difficulty it is to audit a consensus protocol? I know that Tendermint is extremely simple and is now like well tested and well understood. But how is the process for a team who wants to go make their own consensus protocol and have it audited? I heard it's like very complex, very brutal, and just very hard to make your own consensus protocol. Is just like kind of now you're going in unexplored territory versus like the tried and true Tendermint. So I guess how is it making your own consensus protocol versus tried and true Tendermint?
The point of Tendermint is that it has, again, I'm not sure I've given the right historical background there, but how I would like to see the things is that Tendermint was very much in the sort of open source spirit, in the sense we want to make a consensus algorithm that everyone can understand. So basically, the main mechanism of Tendermint is based on classical work you find in the consensus literature from the 80s. Okay, this has been reviewed and re-reviewed, and the algorithms have been proven by several top experts in the field to understand this. So this is a super solid algorithm. And that's sort of the key idea. It's perhaps one of the most understood consensus algorithms worldwide. So this is part of the security that you get, right? This sort of, it's on a solid academic base. So first thing you have to understand, if you come up with your own consensus algorithm, you're the expert on this algorithm, right? So you have to figure out, how can I, if I want to involve someone, an auditor, how can I make sure that they are able to do the audit, that they understand what is there, right? So it's really a matter of having a proper specification and writing it down, and understanding what are the important factors, understanding that there's most likely timing involved, assumptions on timing, assumptions on what are the faults, how many, and all of that, these kind of things. And this should really be written in a document or in a specification file. So of course, I would advocate for Quint. I think it's one of the most accessible tools right now to write algorithms and to make assumptions precise and make sure that you're not overlooking things. Also, you can sort of directly start to simulate things and try things out and write tests and write scenarios. But at least, you should write it in English. Also, there is already to make sure that you're sort of the proper sort of thinking around that. And really try to understand what you try to achieve there, what you're optimizing, right? There's also a lot, even in the crypto space, there have been a lot of different consensus algorithms proposed that are out there. You should really try to understand what is there. Perhaps there's already something that you can use that more people have looked at. And then, sit down to the work. We have recently also talked to Roger Wattenhofer, who is now working for Solana and has proposed a new consensus algorithm for Solana that was announced a couple of weeks ago. They have written an amazing white paper with proofs, with formal properties that's super detailed there. Also strikes a great addresses the performance requirements that they're having, tries to derive similar sort of performance metrics that they have right now, but with a new algorithm, again based on solid theory. So I think that's the way to go. First, be clear what you want to implement at a very high abstraction level, and only then dive into the code. It's very hard to get all these sort of system level properties out of the code. You need to capture them somewhere else. Yeah.
I also want to ask sort of an off-topic question, since you have like a specialty on consensus. We talked about sort of mechanism when it comes to, okay, you built this application with smart contracts, but then it requires bridging and trust of another chain, and that brings on like other trust assumptions.
Yeah.
I want to get your thoughts on. I'm not sure if you heard of Anoma. They have like Chimera, and they have like two BFT systems, which like it's like two separate consensus sets that are like meshed together. I forgot what was the exact description. It was like a raft between two sets. I just want to get your take on that architecture.
Yeah, I'm not up to date to the current design. I talked to them, I don't know, 2 years ago or so. So I think they also are very on a very solid ground, and I think I think also from the sort of their experience, and they have also been involved in IVC, and know sort of the trade-offs there, and there are a lot of gains and a lot of simplifications if you sort of can overlap sort of the validators of two chains in a way, and also in a clever way, sort of to sort of also figure out on what things sort of both validator sets need to do agreement together, and where sort of they can actually run independently at their in their own speed. So, and yeah, I also think that sort of they are going a great way at, in formalization and making sure they capture the properties they want to have, and also to explain it to people in a way that sort of they can follow the ideas. So yeah, I'm a big fan of their approach. They're doing a great job. But I haven't, as I said, I haven't followed the progress recently. But yeah, it's I think everything that sort of doesn't try to invent the wheel from new, but sort of bases their work on sort of solid research. I think they're up for a good start. Yeah.
Okay, and I guess I now want to talk about sort of the tool blocks for auditing. So I guess you have. We'll talk about formal verification and Quint, but is there any other methods or procedures for just auditing in general?
I mean, as I said, in general, for us, the main point is to figure out at the system level what the system is supposed to do and describe that, and in terms of properties, try to understand what is the environment. Sort of, typically it's not only users, right, but it's also other system you're interacting with, and capture these requirements, what the system is supposed to do, and most importantly, because this is super important for security, but not typically the first thing that comes to mind. You have to talk about what the system is not supposed to do, right? You shouldn't if you're not authorized to withdraw money, you shouldn't be allowed to withdraw money, right? So with all the sort of this all these things have to be clear what you're doing, what you're not supposed to do. And yeah, that's what we're doing. We're calling this sort of requirement document, calling it threat model, basically where we write all these properties that the system is supposed to satisfy. And then sort of we link it to the actual implementation and sort of figure out, in the design, in the architecture, where could be potential problems to these functionalities, and this sort of guides our sort of code analysis. So of course we're doing we do standard checks on the code, and propose sort of if we see something better, software engineering practices, all these kind of things. But it's primarily, I would say, guided somehow by the system level requirements. It's also something that I think gives the most valuable feedback. And as I also said in the beginning, it's good to report back why something is working, and not only that something is working. I think this is the main process that we're having. It's sort of driven by the system level properties, and then goes into the analysis. Yeah.
As someone who sort of works in the security and auditing, and you have to like check all these people's codes, how is your feeling around languages in general? Sort of what languages do you prefer? Is it certain languages for certain jobs? I'd like to know sort of your preferred languages on the security and auditing side for the consensus application level. And
Yeah.
let me think.
So
Yeah.
I'm not auditor, so I'm not sort of doing this code analysis on a daily basis. But what is sort of obvious if you compare languages is that, of course, I don't know, if I look at the smart contracting in Cosmos, which is based on Golang, compared to Solidity, it's just that there's much more code in Golang. Right, it's much more concise in Solidity, and it's much sort of because it's in some sense it's more abstract, and therefore it's also more easier to grasp what it's going on there, right? So there is I think a benefit to that, to having sort of a higher level language that takes a lot of the functionality for you, takes a lot of the responsibility from you, right? The viewer lines of code you have to write for functionality, the viewer opportunities there are to introduce bugs. And then, of course, we are all, I think, big fans of Rust. We just know that a big chunk of problems already eliminated just by the fact that it compiles, right? Memory safety, all these kind of things is there. But in general, we have done audits in all different kinds of languages, Solidity, in Golang, in Java, in really Rust. So that's, we were doing all of this. But as I said, I think sort of just sort of the level of abstraction. I think it's important also for the conciseness and the understandability. And understandability is a big factor of auditing, but also of crypto in general, right? In theory, you want everyone to understand your smart contract. So it would be great if it would be concise and fits on the page. So yeah.
Okay. And so I guess now we go into common misconceptions and the questions that I didn't ask, but I should be asking around auditing. So
Okay.
Are there any ones that I missed?
I mean, one thing that sort of comes to mind, I already sort of hinted this several times here, is that audits have to come at the end. You have to finish implementation, you have to do code freeze, and then you do an audit. And I think that's something that we'd like to change a bit the way people think about audits. Because there are, as I said from the very beginning, there are these two questions, right? Am I building the right system? Is one question that you can very early ask. And you can ask someone to take a look at this and look at your design and make sure that sort of the assumptions you're making about the environment, the way you build the system, the way you're planning to handle concurrency is sound. And the earlier you involve or you make sure that the system you're building is correct, I think it's the most beneficial in terms also of the money you're spending on the project. right? Because if you're sort of start to implement, you're not sure whether you're building the right system, and then you've done your first version and you hit the wall, or you figure out there is a corner case that you have missed, and then sort of you have to redo parts of these things, and you're not really sure where you are, or you figure out, oh, I have a performance problem, so I should sort of optimize the performance, but I'm not really actually sure what the system is doing. So what I'm building here. So I think this is really something to keep in mind. I really think that also if you see sort of security and correctness as a long lasting thing, I would really like to push to sort of ask companies to think about this in advance and involve people more earlier, right? If they have design documents, design there, and involve do an audit on that, because I think it's as important. And once this is settled, you're sort of a solid basis. So I think that's one misconception, that it's sort of after the fact. I think there are many other ways to interact with, and as also explained, the threat modeling we are doing, which is we're not really looking at the code at this stage, because we need to understand what you're building, and so therefore there's no reason to do this. Yeah, that's one thing that comes to mind. And the other thing I think is this, which is very intriguing to me. It's the cost of an audit. That's something very interesting, right? So I think we all know about exploits and vulnerabilities that where tens or hundreds of millions of dollars have been lost, right? And now, if you sort of do this thought experiment, you run this, you have a project, and someone comes to you and tells you, look, there's going to be an exploit next week. You're going to lose hundreds of millions of dollars, and I can tell you now what is the bug, how much is it worth? And I think that's a very intriguing question. How much sort of are you willing to invest into your security? And I think that's also, this defies also a little bit human thinking. What price are you willing to pay there, and to get the best people to do that. And it's also, I also like to think about this. And you see this, right? When we in internal project or external, doesn't make a difference. Now, if you find a bug in the system, before it has been put in production, you fix it and go on. There's not a lot of emotions around it, right? But if you would find the same bug after it has been put in production, or even you're finding the bug by figuring out that it has been exploited and money was lost, there's a lot of anxiety, right? And you are sort of willing to put a lot of efforts, and people are they have to work on weekends and all this to get this out. So, and this is really sort of interesting, right? So even if we do audits and or internal things, and we find bugs that might be very expensive down the line, it's not as valued, and it's also understandable. But sort of this is sort of the thing here. I think really people should understand the sort of the risk that sort of they're sort of doing here, and then running the software, and the risk the users are taking, and how much sort of they want to invest into minimizing this risk. I think that's especially in crypto, where there's a lot of money in the system. That's something to keep in mind. And I think that's the main misconceptions.
So to build secure systems, you first need to design them, like specify them, and then you write the code, and then you get it audited. How many teams kind of just get it audited, and then you kind of realize, ooh, you built it all backwards? Has that ever happened?
It happens, yeah. It's people sort of sometimes, because sort of the focus is wrong. So they might have teams might have an edge in a certain technology, and they want to focus on this, and this is also sort of how they market it. But there is some part of the design they haven't thought about, for example, and so that comes back. Also, perhaps I don't think that we are necessarily. Perhaps this is not the point where we are involved, right? In the terms that when they are figuring out problems, they typically somehow fix them, right? They come to us already when they have some level of confidence that it's right. But the question is, how long did it take them compared to how long it should have taken them if they sort of spent a little bit more on the design phase in the beginning. But yeah, sometimes it happens that you find protocol issues on the code side, and so it's definitely there, and still people are happy if you find things and they can fix them. So that's I think that's a good thing. Yeah, and we work together to figuring out what went wrong and what to do there. So yeah.
What I hear sometimes is they get a couple of off the shelf components. They then like put them together, and then they kind of realize through just scope creep or whatever that, oh, we kind of need to rebuild everything in Rust because like we kind of hate this like amalgamation that we built. I guess that's the part where you first need to specify what you need, and that's where scope creep no longer that's what formal specification does. It sort of just,
Yeah,
I guess, boxes it up cleaner.
I think so. Yeah, that's the main point. You should figure out the components, figure out the environment of your system, what you're expecting there, and go from there. Right? You do the design. You do whatever helps you and convince that sort of this. Even if you just put together components, why putting the components together works, and I think this why is also how the interconnections are, right? Sort of if these components, this component A is doing its job because component B is doing a particular thing. And now if you figure out at some point in the process, actually component B is doing something completely different and I was misled, then at least you know where to sort of to do it. But you should go back to the design. I think the important thing really is to, if you figure out something like this, go back to the design, take a step back, breathe, and figure out what happened there, and not sort of try to patch the software somehow without having the bigger picture there. So, and yeah, I think really sort of this sort of design work and thinking at the beginning. I think it's really important also to do it at the higher level. The code is very detailed and is it very easily draws your attention away from the conceptual things, right? If you don't like formal languages, at least draw diagrams. That can also be already helpful. Figure out what data are stored where and who sends data where. These kind of things. But it's really important to have a mental picture of the whole thing and why you believe it's working in the very beginning. And also it helps you to locate the bug. That sounds weird, right? But if you have two components that are interacting and they're not doing what you thought they would do in together, it's not. You don't know whether the bug happens in component A or in component B, or in the compositions. It's really understand what I am, assuming about the interface and what is right, and we have where also to fix it. What is the best place to fix it? And for all this, it's very important to have a very high level view and understand what the checks are done where, all these kind of things. So I really believe that this doing this work and writing it down helps you really to sort of codify your thinking, codify why you are, I believe your system is doing the right thing, and then you take it from there. It's still, yeah, that's the most promising way. Yeah.
So we've been talking about like planning and specifying, but there's been this new trend of AI vibe coding where you kind of just like you don't really do any of that stuff. What is your take on that as someone who works in security, just like vibe coding?
Uh, I'm not sure. I follow all the trends there. I don't think that uh, you can get rid of the thinking in the design process. I mean, if you're just copying what someone else is doing or something like this, perhaps it works, right? Or you want to do some optimizations. But in general, the systems we are building here are so complicated that it's for the human mind impossible to figure out, or very hard to figure out all the interactions. And as I said, I have an academic background in formal verification. A lot of the verifications questions around this about distributed systems, they are theoretically undecidable. They are unsolvable. So there's no computer program, and this is like a super hard, rock solid result, who is going to decide whether the program is correct or wrong. And artificial intelligence doesn't sort of solve this for you, right? So if you're not able to convince yourself that the solution that the AI produces is actually doing what it's supposed to do, no one can, right? No tool can, no verification can, and perhaps the AI can tell you yes, it's correct, but you don't know whether you trust it. So I think the only way that we have developed over since the conception of computer science is to do abstractions, do modularizations, cut down your problem into sub-problem, understand how they interfere with each other, do this sort of cutting these problems until they are so easy to understand that you're convinced, and that you can convince your 10-year-old niece that it's correct, and then you move on, and then you dive into these individual parts and do the same thing there. So I think there's no way out of this. So if you're if you care about correctness and you care about that the system is doing what you want to do, in the end you have to convince yourself. No AI can sort of help you there. And I think that's sort of the important point here. So, and again, it's a different. There's a different. Yeah, these are two questions, right? Just coding something or coming up with a design are two different tasks, and especially the design task is I don't believe in automation yet. So, but let's see. Yeah.
Yeah, I guess it's time to wrap it up. So, people who are interested in audits and want to get audited by Informal, how can they get started or who to reach out to?
Yeah.
And we'll finish this.
Sounds good. Yeah, just reach out there by email, audits@informal.systems. Also, we have a webpage, informal.systems. Should be easy to find. We're also on X, so follow us there. And yeah, just reach out. I think there's even a form on the webpage. So I think it's informal.systems/security-and-engineering, where you can get in contact. So yeah, we're looking forward to it. We look forward to become part of the team for the project.
Anyways, thank you so much. Had a great conversation.
Likewise.
Learned a lot about just auditing. So thank you so much, Josef.
Thanks for having me. Thanks a lot.